Hi everyone, I'm Cody Root, and this is the Church of Logic. I'm pretty excited today. We're going to talk about self-reference and the halting problem. Last time I talked about how there were problems about computers and programs that other programs wouldn't be able to solve, and I hinted that the reason for this was this ability that programs have to simulate other programs. But I left it a little vague, and today we're going to try and sort of make this precise. And to do that, we need to talk about self-reference, which honestly is probably the funnest, most interesting, and exciting thing about mathematical logic. So I'm pretty excited about this one. Let's see. So the background is, we've seen all these definitions of computability. They're sort of all equivalent in some sense. They all seem to capture something reasonable about programming. They all seem to be like, hey, this is pretty reasonable. I can imagine carrying out all these steps as a human being. And now, of course, we have computers that can carry out all these steps. They're very simple steps, symbolic. Look at a symbol, decide what to do, write new symbols. So, okay, we also saw that this kind of was unexpectedly powerful because you can use that machinery to take in instructions that represent another machine and execute that. So, how do we use this power to build an impossible problem for machines to solve? I said it last time, but let me repeat it. The impossible problem for a machine to solve is the following question. Give me a program and give me an input to this program and say, hey, does this program halt when it's given this input? That is, does this program run for a certain amount of time and then stop running and return an answer? And of course, the other possibility is it keeps running forever and it never returns an answer. And the question we want to answer is, is it possible to look at a program and an input, determine whether it's going to halt for that input? And the answer to that is that it's not possible in general. It's possible to do it for certain programs, right? Of course, if I take a program that immediately halts, or if I take a program that, in a first state says, hey, let's go back into that state and keep doing that forever, then, we know the answer for those programs. One of them halts immediately, the other one runs forever for trivial reasons. But the question is more in general, for any program, can I determine the answer? And we want to determine the answer by using another program that takes this first program as input. The answer is no, it's not possible. And kind of the reason for that is because programs are too complicated. And so there's this kind of idea that a program isn't powerful enough to analyze, this arbitrary complexity. So the proof goes something like this, and I'm going to give the main idea, and then I'm going to dig down in the details a little bit. The proof is this. Imagine you did have a program that solved this problem. You did have a program that took as input the description of a program, the description of the input, and returned yes, always, if the program halted on that input, and no, if it didn't halt on that input. All right. Again, I haven't really explained what answering yes means or answering no. You could just say, oh, it returns 0 if it halts and 1 if it doesn't halt, or the opposite or whatever. But it's not hard to imagine like what it means for a program to answer. So imagine we have this program, right? It takes in input, it says this halts on this input, this doesn't halt on this input. And what we're going to do is we're going to build a program that defeats this first program, right? It defeats it by creating an absurd situation where it couldn't have been possible for that initial program to exist. All right, and this is kind of a subtle point, but the idea is if we show that there's a certain input that makes that first program not behave the way we expected, then we get a contradiction. And so that first program couldn't possibly have existed. All right? So how do we do this? Well, we're going to build a second program. So the first program is fixed. We assumed it exists. But the second program, we're going to use it to defeat the first program. And how are we going to do that? We're going to take this second program and say, okay, we're going to describe a program that does the following things. it takes the halting program, the one we supposed existed, and it runs it on itself. All right? So the second program takes the first program, the halting one, and it runs it on itself. And I'm going to explain how to do that, but just assume for a moment that it is possible for a program to inspect its own code. All right? And you can imagine in C, that's pretty easy, right? In a C program, you can just open the file that contains the source code of your own program, right? So it's not absurd for this to be possible. And you're going to take this halting program, you're going to run it on yourself, and you're going to see what it answers. You're going to see either it says, yes, this program halts on this input, or no, it doesn't halt on this input. And this input, again, in this case, is yourself. Okay, so you do this, and then you invert the answer. That's the brilliant point. You take the halting program, you run it on yourself. If it says, yes, this halts on this input, then you just loop forever. If it says, no, this doesn't halt on this input, then you immediately halt. So you see you've inverted the answer. You've taken this halting program, you've run it itself to predict what it was going to do, and then you did the opposite. So you're sort of defeating this predictor program by asking it what it would predict and then doing the opposite, right? And the crucial point here is that we can simulate this hypothetical halting verifier, right? If it exists, then we can simulate it. And, the second crucial point is that you can take a program and you can assume that program knows what its own code is. Now, this is a subtle point, I think, and it is kind of surprising. Though I've given you sort of an idea how this might work. A C program could open the file that contains its own source code and could examine that source code and do whatever it wanted. It's a little subtle, right? You could say, well, this is a little weird, first of all. How does C even do that? And second of all, what if these Turing machines or these lambda calculus paradigms or this good old number encoding thing, none of those had the ability to open a file on a computer. So how do those get to look at their own source code? And the answer is there's a kind of very general approach that allows you to assume that any program can have access to their own source code if they want to. This is a very clever thing. Basically, the idea is something called a quine, and it's explained beautifully in this Gödel Escher-Bach book that I believe is the inspiration of almost half of people that go into logic to actually do that, go into logic. But the idea is that, yes, a program can always have access to its own source code, and the trick here is this kind of diagonal trick where you sort of build up a string and you say, okay, well, this string is going to be my source code, and it's going to take as input again a string that its own source code. So this is kind of a subtle point. I don't think I'm going to completely explain it here because it's actually a little bit surprising. But the basic answer is you can build, in any language that has a print statement, say, a program that prints out exactly its source code, right? So you can do this in Python. Something I really do want to insist on is these programs that take in as input other programs, those are very real. There are tons of programs out there that actually do this. For example, whatever system you're listening to this on, this system has an operating system, right? And what's an operating system? It's literally a program that runs a bunch of other programs, right? So this is very real in everyday life. There are programs that take in other programs and do things with them, like run them. So this is very feasible. And what this proves is that there are other things you want to analyze about programs that aren't feasible. My argument just proved that you cannot take in a program and ask it whether it's going to halt on a given input. And this impossibility, I mean, Turing realized it, but pretty much everybody else in logic realized it as well. This impossibility, this fundamental obstruction of being able to analyze programs with other programs was a deep limitation, and it was an important one in logic. Basically, you can sort of say, hey, any logic that's reasonable, that proceeds by using computability, which is all the logics we had described up to the point, and even up to today. And we believe it's the only way to describe a logic. All these logics that proceed by computable rules, those have fundamental limitations, and those limitations are very fundamental. There's no way to get around it other than to go beyond computability, and we really believe that that's not possible. There's very, very little reason to believe that we can do uncomputable things. So this was a real breaking point. This was a very, very fundamental observation, this fundamental limitation, and it was one of the big it was kind of a landmark event in logic that there were things that were just not possible. So at some point I'll talk more about how these limitations influenced the rest of the field, but I think this is one of the exciting things, and I think this ability to talk about self-reference, it's one of the exciting things about logic.